third conference of this type, and it's always a real pleasure. So thank you very much for the invitation, and also thank you very much for letting me give the first talk. This is really very nice. Right, so first things first, happy birthday, Michelle, and may you live another 75 years, and I wish you all the best for the next 75 years. All right, let me go back for just a second. So you're very welcome. So the talk that I'm giving today is kind of chapter 2 in a story that Mike Jacobson began at the same conference about 2 years ago. This was ongoing work at the time with 2 of our former students. Nicholas Rollick is the last name here. He started working on this actually all the way back in 2014. And Christian Bagshaw worked with us for the last few summers and has now just gone off to graduate school in Australia. And the work is now almost finished. And when Mike gave this talk, we had done a lot of the conceptual work and some of the algorithms, but we hadn't really finished our big computations yet. And so I want to follow up on Mike's report from then and report on the computations that we did. So with apologies to the people who heard Mike's first talk about this at the conference at ICCGNFRT in 2019, a lot of this is going to be repeated. So I know several people were there, of course, Kalyan and Azizul, I think Michelle and various other people. So apologies to you, maybe fall asleep for the first half of the talk, because a lot of it will be kind of a repetition from that talk. But then I figured, on the other hand, there are a lot of people here, especially the students at the Institute, who probably haven't heard any about this. And so I figured I should better start sort of from scratch. So the title of this work is Constructing Imaginary Quadratic Fields with Large N-Class Rank. So I think the first thing I'd like to do is explain some of the terminology and some of the notation and terminology in this title. So just to establish some notation, we're going to work with quadratic fields. So this is the general form of a quadratic field. So delta here is a discriminant. It's an integer that's going to 0 or 1 mod 4. We're also going to assume that it is fundamental, which means either delta is square free, or it may have a factor of 4 in it, and then we divide that out, and then the rest has to be square free. And we will also only work with imaginary quadratic fields, which means that the delta is negative. So the discriminant is negative. And then the quadratic field of discriminant delta has this form. 1 and square root of delta is a basis, and it's basically a rank 2 dimension 2 vector space over the rational numbers with basis 1 square root of delta. But of course, it is also a field. So these are the objects that we'll be working on, these quadratic fields. And then the topic of this conference, well, the ideal class group, it's a finite abelian group. It's, of course, the ideal classes consist of the ideal classes of fractional ideals modulo principal ideals. There are several ways to represent it. Normally, that we will be representing it via unique reduced ideals. So in each ideal class, there is a representative that is basically small. It has a small representation. Its norm is essentially bounded by the absolute value of square root of delta. And these things are easy to find and to compute. So that's how we'll represent it. And this is a finite abelian group. So you would somehow think that computing finite abelian groups are like a very simple thing, but it's not. It's actually very difficult to compute. What do we mean by computing the class group? Well, as a finite abelian group, you can represent it in the standard finite abelian group representation via its elementary divisors, where the class group is this direct product of cyclic groups, and each di plus 1 divides the previous di. And that's a unique representation. And so computing the class group means computing these di's. And for a given integer n, positive integer n, the n class rank is the number of elementary divisors in the class group that are divisible by n. Okay, so it's the number of these di's that are divisible by n. That is the n class rank. Sometimes we also just call it the n rank. So it's the n rank of the class group. And this is the object that we're interested in. So what do we know about this? Well, the answer is we don't know much. We really don't know much about these n class ranks. They have been the subject of quite intense research. For n equals 2, that's the marked exception. The n equals 2, that case is very well understood. It's very classical, goes back to genus theory. And the number of the 2 class rank is basically determined by the number of prime factors of the discriminant. But after that, we don't know much. Now, when n is an odd prime, we have the Cohen-Lenstra heuristics. This is a heuristic. This is not proved. And it predicts that the set of negative fundamental discriminant such that the p class rank for an odd prime p is equal to a given integer r has positive n density. And this density is essentially more or less p to the minus r squared. So you see here already as r, the p rank grows, or as p grows, this number gets very, very small. So these things are pretty rare. Now, this is a heuristic. This is unproven. It seems true. It's been numerically verified extensively, but people have not been able to prove this for a single PR pair. So it's strictly heuristic. But it tells us that quadratic fields with high P rank, P class rank, are quite rare. Now, some early work of some infinite families and also examples. So the first one who worked on this was arguably Nagel, who managed to find an infinite family of quadratic fields that has basically positive n rank. So the class number is divisible by n. This was extended by Yamamoto to get the n class rank above 2. Craig in 1977 for his PhD thesis gave a construction of fields where the 3 rank is at most 4, and Mestre later on a construction where the 5 rank is at most 3. So that's pretty much it. There's been lots and lots of work about finding families and finding examples of fields with high P class rank, including work by Kalyan and Azizul and other people who are here. But this is sort of the earliest constructions. Now here are some records. So for 3 rank, the 3 class rank, the record is 6. This is due to Lorenta and Quer from 1987 using a search method due to Diaz, which I'll say more about. For P equals 5, the record is 4. This is due to Renate Schiedler from 1983. For 7, the record is 3. This is Solderich, 1977. 11 is due to Leprevost, 1993. And then the last 3, 13, 17, and 19 is work by Mike Jacobson with some of his students. These are the theses of these students. Ramachandran and Mosunov were both students at University of Calgary, wrote their thesis on class group computation. So they basically computed class groups and they found these new records. And that's about it. So, I mean, above 19, it starts getting very difficult. And one of the big questions is the P class rank unbounded? And the answer is we don't know. We don't even know if it's ever bigger than 6. So that's a long ways from being unbounded. So we're really very blissfully ignorant about these things. And one of the problems is that these examples are very rare. You have to construct these things very carefully. If I give you a random quadratic field, I just guess a negative fundamental discriminant, it's going to have very small P class rank. Okay, so the goal for this work was to construct imaginary quadratic fields with large n class rank, where large is in the eye of the beholder. And what we wanted to do is we wanted to do it in such a way that the discriminants are small, so that the discriminants are as small as possible in absolute value, because we wanted to do computation, and computing with large discriminants is just difficult. Okay, and so just to sort of in anticipation of our results, we used the Diaz 1978 algorithm. I'll get into that in a little while. We generalized that from 3 rank. Diaz only did this for 3 class rank. We generalized it to any odd n. We found the smallest known example of a field with 5 class rank equal to 4. There were examples of 5 rank 4 before, but they had larger discriminants. And we found the first examples of 7 class rank equal to 4. And we didn't just find a handful of them. I think we found something like 67 of them. So we found quite a few. Okay. And Mike Jacobson, as I said, first reported on this work in 2019. And so now I want to follow up and talk a little bit more about what we did and how we did it. So there are various ways that you can find quadratic fields of high n class rank or P class rank. The first thing is you just compute the class group for all discriminants up to some bound. Okay. So this was in fact done. Duncan Buell did this extensively in the 1970s and 80s. And computed all the class groups for discriminants up to this year, so 2.2 billion. This was extended in the 2 theses out of University of Calgary that I mentioned before. first to about twice 10 to the 11, and then a little bit bigger to 10 to the 12. And so basically they computed all the class groups for all those discriminant up to these bounds in absolute value. The advantage of this is that you can guarantee a minimal discriminant for each n class rank. You just sort of check when you get the first n class rank of whatever you want it to be, and then that's your smallest example. So you can guaranteed find minimal discriminants, but the disadvantage is that you need to compute all these class groups. So that's a lot of work. Computing class groups is not so easy, and there's lots of them up to big bounds. There's one exception. There's a wonderful tabulation algorithm to Belabas from 2004, where he tabulates both real and imaginary quadratic fields of discriminant roughly up to 10 to the 10 with positive 3 rank. And he does it via cubic field tabulation. He does not make use of class group computation, but that's the only exception that we know. So that's the first approach. The second approach is to find parameterized families. So this sort of follows in the footsteps of Nagel and Yamamoto. So you basically derive such families from the solutions to a norm equation. We'll see that norm equation in a little while. And this was Nagel's and Kuroda's approach, and then Yamamoto, Shanks extended this, and lots of others, various families. Another approach to constructing such families is using geometric methods related to curves, elliptic and hyperelliptic curves. This was done by Mestre in 1983, by Schoof also in 1983, and by Leprevost in 1993. And you use basically torsion points on curves or on abelian varieties. Those are the two approaches. And Gilibert and Levin, in a wonderful paper from quite recently, 2020 and 2021, unified both of these approaches under a geometric framework. I believe Gilibert is actually also speaking at this conference, and he's also a regular at these conferences. So he's a friend of the show, so to speak. He's a friend of this conference. So that's another possibility. The advantage is that it can be relatively simple to construct such a field, especially the ones that come from the norm equation. And you can also use this to derive lower bounds on the densities of such fields. But the disadvantage is that the yield is not very high. You don't get minimal discriminants, and you don't find very many generally. So you don't have a good yield. So there's advantages and disadvantages to all of these approaches. And then the third approach is, so we had class group computation, we had this construction method. The third approach is just the targeted search, where you look for deltas that are good candidates, and then maybe or maybe not, you compute the class group. And this approach was taken by Diaz y Diaz in 1974 and 78 in his PhD thesis. And he did a very efficient search based on this norm equation. And it produced many, 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 many discriminants with positive 3-class rank, and even 3-class rank at least 2. I mean, the algorithm is like a fire hose. It spits these out at an enormous rate. The examples that he got are not necessarily guaranteed to be minimal, the discriminants, but they're pretty small. So this is a good method. And then Lorente and Quayer, who currently hold the 3-class rank record of 6, in 1988 produced this record. And what they did is they first tried computations using certain families. Then they tried the geometric methods, and then they tried the Diaz y Diaz search algorithm, and that was best. And that's how they found their record. So they tried which one worked best, and this was the best one. And so this is what we opted as well. We chose this, and we decided to go with that and work from there. So we started with the Diaz y Diaz algorithm. Now, the Diaz y Diaz algorithm is based on Kuroda's and Yamamoto's idea as follows. So Kuroda gave this result with the following idea in 1964. Suppose you have an ideal M, and it represents an ideal class of order N in the class group. Then M to the N, of course, is principal, and it has a generator, and this is then what the generator looks like. This is what the generator looks like. And then if you take norms on both sides and bring the forward to the other side, you get this norm equation. And this is the Diophantine equation that you start from. And the idea is to search for solutions to this equation in some intelligent way. Okay? So M is the norm of the ideal, and this Y and the Z are these quantities. And then you see here, if you write it like this, then you see here that there's only finitely many Ys and Zs for each ideal norm. All right. And then Yamamoto improved on this result, and he managed to find 2 solutions to this equation. Now, of course, just because you find 2 solutions, that doesn't mean that the 2 ideals represent independent ideal classes, but he found conditions that guarantee that these 2 ideal classes are independent. So you have an n-class rank of at least 2. So that was Yamamoto's work. And this is the basis of the Diaz y Diaz algorithm. And so DRC-DS wrote this algorithm for n equals 3, for 3 rank, based on Yamamoto's idea. And in a nutshell, the idea goes like this. So he picks an M, that's your ideal norm, and he picks a T, that's just a parameter, and then he forms this quantity here. And now he factors something. So he writes the T as a product of two things. He writes the N as a product of two things. And then he puts Y to be this quantity. That's the Y from the equation before. Okay. And now he looks at this. You consider this equation. So if you form the quantity 4m cubed minus y squared, then that determines Z and delta. Delta is the fundamental part of this, and Z squared is the square part of this. And if 4m cubed bigger than y squared, then you know that delta is a negative discriminant. And then it turns out that you have two solutions to this norm equation, these two solutions here. So this was DRC-DS's contribution. So again, now you have these two solutions, but they may not represent independent ideal classes. So in order to test that these ideal classes are independent and gives you a 3-class rank of at least 2, what he did is the following. A sufficient condition for this is the greatest common divisor of both these ideal norms, M and M plus T, with this Z has to be square free and it has to divide the discriminant. Okay, that's a sufficient condition for them. So that's a necessary condition rather, that's a necessary condition. And then when you have that, you check the independence by taking the bigger of the two norm and checking that it satisfies this bound. Because then the corresponding ideal is a reduced ideal, and the one with M is even smaller, it's also a reduced ideal. So now you have two distinct reduced ideals, so they have to represent distinct ideal classes, because each ideal class contains a unique reduced ideal. And now you know you have two independent ideal classes, and so you have a 3-class rank of at least 2. Okay, so this was his idea. And if you want to get a 3-class rank of bigger than 2, then you just collect for any particular delta, you collect as many as you can and see if they're independent. And he found many examples of 3-class rank 3 and up either. Okay, and so we started working on this. Nick Rollick started working on this in 2014. The first thing he did is he took DRC-DS's algorithm and ideas and generalized this to arbitrary odd primes P. Okay, and then our second student, Christian Bagshaw, started working on this in the summer of 2018. He worked on this for 3 summers. He generalized it to arbitrary odd numbers N. And then he made a bunch of improvements to this algorithm. It's these improvements that I want to talk about. So in addition to the generalization, he changed the way that you search. So DRC-DS basically did the search space. So he searched over M1 up to a given bound. That's one of the ideal norms. And then this parameter T up to this. And then he determined M2. And Christian changed the order of the search a little bit. That seems like a minor little trivial thing, but surprisingly, it improved the algorithm substantially just by changing the order in which you search for things. So that was the first big improvement. The second big improvement is, let me go back for just a second to the previous slide. In DRC-DS's case, he only ever considers one Z value here. So this quantity Z squared delta has to be the same all the time. So here's Z and delta, and here's Z and delta. It's the same Z. The M and the Y changes, but the Z and the delta stays the same. And Christian's idea was to allow different Z values. And so in particular, in essence, what he was looking at, what he did is he introduced this additional parameter here, a lambda 1 here and a lambda 2 here. And then he allowed different lambda values. And DRC-DS is essentially just putting these two lambda values equal to 1. That turned out to be a very, very big improvement. The yield is much, much higher, especially for bigger N. This worked really well. So that was the second big improvement. And I point out, by the way, that if you equate these, if you equate these two, if you subtract them and you rearrange terms, you're going to see that the difference of the left-hand side here is the difference of squares. And the difference of squares always means a factorization. Okay, so he looks for factors of this quantity here. So the approach here is like this. So you search over some ideal norms, M2 and M1, up to a given bound, and you fix a lambda 1, lambda 2 pair for one round, and then maybe later on you do a different lambda 2, lambda 1, lambda 2 pair, and then a different one, and so on. But we fixed them for now. And then for each of these M pairs, you factor this. You write this in some factorization, A times B, and then using this equation, A times B is this difference of squares, you set your Y1 to be this and your Y2 to be this. And now, if they're integers, then you form these equations for 1 and 2. This determines a z and a delta. Okay, so that gives you a z and a delta, and you hope that the discriminant is negative. And now you have two solutions to this equation, one for M1 and one for M2. Here now there's this additional lambda, okay? And now you still need to figure out whether these two give you independent ideal classes. So you need that GCD condition again. The only difference is that instead of taking the GCD of M and Z, you take the GCD of Mi and lambda IZ, but other than that, it's the same. And now for n bigger than 3, the independence condition becomes rather restrictive. Even if n is prime, this turns out to be the condition. So M1, again, this says that it's a reduced ideal. This says that all the powers of the second ideal are also reduced. The powers and the inverses of the powers, okay? And then you also need this divisibility condition. And under those circumstances, this ideal is reduced. But you see here already that that's a very restrictive condition. For n equals 3, this quantity here is 1, so we didn't need this. But for bigger n, we need this extra condition. And you see here that only allows for a very small range of M2 values. So computationally, this is a pretty restrictive condition. So the bound on M2 for this, when n exceeds 3, when you look at n class ranks bigger than 3, it's just too restrictive. The M2 is basically restricted to the n minus first root of delta. And you just don't find enough stuff. You can run this algorithm and you just don't find anything. It's way too restrictive. And that leads to the third improvement. Instead of using this independence condition, you just do an explicit independence test. So what you do is when you have your two solutions, your two ideals, you just check if they are independent in the group theoretic sense. So you look at the group generated by the two of them. That's a subgroup of the class group. And then you check, you hope that they're independent, even if they're not independent. As you find more and more solutions to a given delta, you keep adding that, and you only add them if they're independent with the previous stuff. So you guarantee independence this way, and you can even keep all these results and try the run again with a different lambda pair and collect more and more and more of them. And that's how you collect independent solutions. And that also gives a really good way of detecting higher n ranks. So not just 2, but maybe an n class rank of 3 or 4. So that was his third big improvement. But then you see immediately that this requires a lot of ideal arithmetic, right? You need to do all these power products. You need to do all these independence checks. And so you need to compute a lot of power products of ideals. And so you need to be able to do efficient ideal arithmetic. So one of the things that we did is we found a Z basis for these ideals. We found a Z basis of this ideal. Now, I think this was one of those results that was known as folklore and used a lot, but nobody ever properly wrote it down. So we wrote this properly down, and we represent these ideals, M, these reduced ideals, in terms of a Z basis. And here's the Z basis. So this ideal has this form. So M is the norm. And then the other basis element is x plus square root of delta over 2. And this is an ideal and not just a rank 2 Z module if and only if delta is a square modulo 4m and this x is a square root. So what you need to do is you need to compute a square root of delta modulo 4m, and that gives you a nice Z basis. And here's how you do this. Now, this looks rather ferocious, but don't look at the details. All I want you to take away from this is a really easy computation. You compute a GCD, you do a bit of division, you do a modular inversion, and you do a Chinese remaindering. So this can all be done with basically some sort of first-year elementary number theory machinery, right? So it's quite easy to do this. So now we have the Z basis, and so now we can perform very efficient ideal arithmetic, and we can actually explicitly test whether the ideals that we get from these norm equations are independent and generate independent ideal classes. So that was his third big improvement. And the fourth big improvement, remember, we have to factor this quantity. Now, when this quantity is small, factoring is not so bad, but as the M values grow, this becomes a very big quantity, and factoring it becomes very expensive. And so what we do is, use a technology or an approach that is used very, very commonly when you have to factor sort of modest size integers. For example, it's used in class group algorithms, it's used in integer factorization, it's used in discrete log computations and so on, in class groups and so on. And it's using a sieve. So you generate a list of primes, the so-called sieve primes. They are reasonably small primes up to some sort of sieve bound, which is experimentally determined. So it's just a list of primes. And now you're looking which of these primes divides this number here, right? This is the number we had to factor. And when we factored it, we had a difference of squares, and that gave us our Y values. And so that gave us our ideals. Okay, and now, so for each of these odd sieve primes, the first thing you do is you compute all the nth roots of this quantity modulo Q. So why is that? Well, if Q divides this quantity here, then this is congruent to 0 mod Q. And when you rearrange terms and get rid of the 4, let's just assume Q is odd for now, then you will see that m1 to the n divided by m2 to the n is lambda 1 squared divided by lambda 2 squared. Is lambda 2 squared divided by lambda 1 squared. So lambda 2 over lambda 1 squared is an nth root. So m1 over m2 is an nth root of this quantity. So you compute all of these nth roots. And then that gives a relationship between m1 and m2. So Q divides this quantity if and only if m2 is congruent to one of these nth roots times m1 modulo Q for any of these roots. So when you have an m1, that determines the m2 and vice versa. And now here comes the sieving part. So if you remember the sieve of Eratosthenes, you remember how that works, right? You generate all the primes up to some bound. So what you do is you start with 2, and then you cross out all the multiples of 2. But there's no factorization going on. You just keep going up in increments of 2 and deleting all the multiples of 2. And then you keep doing this with 3. You go up in increments of 3, remove all the multiples of 3. And in the end, all that's left is the primes. And so this idea of going in increments of primes is the sieving, and we do something similar here. So if we have a root like this, F1, M1 and M2 is going to 0 mod Q, then that Q also divides all these quantities here, M1 plus some multiple of Q and M2 plus some multiple of Q. So all of a sudden you get a whole bunch of other quantities that you know are also divisible by Q. And so you take all these quantities, you divvy out as many Qs as you can, the numbers get smaller and smaller and smaller, and what's left after you can't divide out any more Qs for each sieve prime, for each of the sieve primes you do this, what's left you factor with the good old-fashioned pedestrian way. And so you have to factor a lot fewer numbers, and the numbers you factor are smaller. That's the sieve idea. And so that was the improvement 4 that he did. And so what you do is, as I said, you take this quantity, you divide it by Q as often as is possible, and then you factor anything that's left over. For example, we implement this in SageMath, so you just use SageMath's factor function. So that was the 4th big improvement. These were the big improvements that we made to DRC-DSS algorithm. Okay, so if you put this all together, you get the following algorithm. You input a positive integer n, and you want quadratic fields, imaginary quadratic fields, of large n rank. You also input a collection of these lambda pairs. You just determine these, you pick them. Well, I'll say in a minute how we pick those. And then you you input lower and upper bounds on your ideal norms. And then you basically search. So what it outputs is a table of triples. The first entry in each triple is a discriminant. The second entry is the n class rank. And the third entry is actually optional. You can actually compute the class group, or at least the n part of the class group. And you only keep the ones that have n class rank greater or equal 2 or greater or equal 3, whatever your heart desires. And what you do is for each of these ideal norms M1, and then so you loop over all the M1s inside your bounds. And then for each M1, you loop over all the M2s, the other ideal norms, and you loop over each of these lambda pairs. And then you use that solution approach from the norm equation, and you find solutions, you find integers y1 and y2 and z and delta, such that this equation here is satisfied and delta is less than 0. And every time you find one, you store the delta mi pairs in a file, and you sort that file according to discriminants, according to the absolute value of the discriminant. And now for each, and then you have this massive file with all these pairs where delta is a discriminant and these MIs are these ideal norms that give you solutions. And now for each of these pairs, you either ensure that the n class rank is at least 2 via these ideal independence conditions. That works pretty well when things are small. Or you just use the ideal independence test and you count the number of independent order n subgroups via the independent test. So let's say R is that number. And then R is going to be a lower bound on the n class rank. So you found a bunch of independent classes, but there may be a bunch of other more independent ones that you didn't find. So you only get a lower bound on the n class rank. And then what you can do, if your computing power allows it, is you actually compute the class group of those guys, just those candidates that are candidates to have large n class rank. And you compute the class groups, and then you output, whenever you have an n class rank of at least 2 or at least 3 or whatever you like, you output this triple. Okay? So that's putting it all together with all these improvements, including like the sieving is in there and everything. That's all in step 2. Okay. So to recap, what we did is we started with DRC-DS's algorithm for 3 class rank, for high, please 3 class rank. Okay. The first we did is we extended that algorithm to arbitrary odd n. In our tables, I'm going to show some figures and tables. That variant, just the vanilla generalization, is called DYDEXT. So that's extended DRC-DS. Then we improved the search space by changing the order in which you search things. So this is called improved DRC-DS extended. Then we introduced these lambdas to get even more solution. This is called the expanded search. And then we introduced an ideal independence, an independence test for ideal classes. And this is called explicit ind. Okay. And then also there was the sieving as a sort of separate independent improvement. So those were the improvements. And so now this is pretty much what Mike reported. So I'm going to start reporting on some of our computations now. So this is what we did. So we ran our algorithm on values of n equals 3, 5, 7, 11, and 13. So we didn't go any further at this point. So this is what we used. We used different bounds on our ideal norm M1. So the way you do this is you make the bound some sort of power of 2 and you increment these powers of 2 up to, well, depending on what your n is, something like 2 to the 13 or 2 to the 14 or something, right? That's a standard way to do this. And I should really say that when you want to run a large scale computation like this, a massive computation, you have to be very careful how you fine tune your parameters. How do you choose your bounds on M? How do you choose your lambda pairs? In which order do you choose your lambda pairs? How do you, the M bounds I already said, right? When is sieving worth it versus not worth it? When is ideal independence test worth it versus the explicit independence condition, and so on. And you don't want to start a big computation and just run it. You need to experiment a little bit. So there's a lot of experimentation that you run in advance, where you run smaller scale computations and you curve sort of, you fit your various parameter choices and other choices to curves, and then you extrapolate the curves, and then based on the extrapolation, you pick the optimal parameters for your large scale computation. So there's a lot of sort of advanced legwork to be done in this. So that took quite a while. And so, but let me first now show you some graphs. So these are five tables. This is for 3 class rank, 5 class rank, 7 class rank, 11 class rank, 13 class rank. The red curve is just the extension of DRC-DS to arbitrary n. The yellow curve is the improved search. The green curve is the expanded search with the extra lambdas, and the blue curve is the one with the independence test. And you see here for n equals 3, except for the vanilla generalization of DRC-DS, they're all pretty equal in computing. So the x-axis plots the bound on the norm, and the y-axis computes the runtime. Okay, so they're all comparable, except the vanilla generalization is a little bit worse. As your n class rank improves, the vanilla generalization gets worse and worse and worse. So in the end, we don't even consider it anymore. But the other algorithms seem to be performing very, very similar to each other. Now, the picture changes a little bit if you don't look at things overall, the computation time overall, but you look at the computation time per discriminant and you compare it per discriminant. So again, you see that the red one, I mean, it already goes off the chart. Even for n equals 5, it's already off the chart. It's not obscured by this little box here. And initially, the expanded search does very, very well, right? It performs really well. The explicit independence test is much worse initially compared to the explicit independent condition, but it gets better and better and better. And at some point it starts winning out. And the improved search initially does pretty well, but then it actually loses out. So you see here that the green and the blue variant, the one with the expanded search, that's the business with the lambda, and the one with the ideal independence test, they seem to be winning. So those are the algorithms that we focused on our attention on. So we're going to dismiss the other two algorithms, the ones that are represented by the orange and the red line, and we'll just focus on those two algorithms. And so all the computations we did was then with those two algorithms. And so what we did is now we compared this extended search with the lambdas with both the independence condition on the two M's and the explicit condition that guarantees, like the condition on the norms that guarantees ideal independence, and the explicit independence test. Okay, so that algorithm with these two variants, and there's two criteria by which you can evaluate this. One is the overall speed, both the overall speed as I just showed it and the speed per discriminant. But the other ability is the other criterion is the algorithm's ability to find small discriminants. So to find small deltas that have n-class rank at least 2. And here's what we came up with. So for small n ranks, 3 and 5, the explicit condition works well and it wins out, but the independence test does better with small ideals. For n equals 7, they were comparable. You saw that in the figures. But then for the bigger n-class ranks, the 11 rank and the 3 rank, the independence test, the version that uses the independence test, ideal class independence test, the group theoretic test, wins hands down in all criteria, both in speed and in ability to find small discriminants. And in fact, by a long shot, the smallest discriminant found by the independence test version over the other version, the discriminant was smaller by a factor of 4 for n equals 11 and smaller by a factor of 250 for n equals 13. So that is the algorithm to go with if you want to start computing bigger n-class rank, if you want to move to 19 or something, 23, okay? And so in general, the explicit independence test version is very effective at detecting, let me rephrase this. So there was one disappointment, and that is, so this algorithm finds a bunch of independent ideal classes. In general, it finds 2 of them, okay? But it's actually very, very bad at detecting higher n-class rank. It says, oh, okay, I found 2 independent ideal classes, but meanwhile, the actual n-class rank might be as big as 3 or something, or 4. And the algorithm doesn't find that. So it's very bad at detecting higher n-class rank than the promised 2. And I think this is because we're looking for things in pairs. So this is something that we need to look into it. So for example, here's something really disappointing. So for n equals 7, that algorithm didn't report a single example of a 7-class rank of 3 or higher, even though for the bounds that we ran it on, there were 20,000 such examples. It just didn't realize that a lot of the examples that it found with 2 independent ideal classes actually had 7-class rank 3 and not just 2. It's very bad at detecting that. So that's a bit of a downside. So that was more findings. Now, how did we choose our lambda 1 and lambda 2? Well, this is strictly experimental, trial and error. The good news is this works very well. If you introduce these lambda pairs, the search works a lot better. It increases the overall yield of discriminants, and it also finds smaller discriminants. So it's good in every way. The gains get better and better the larger the n-class rank gets. So that's also promising. The bad news is that as you increase more lambda pairs, the cost per discriminant also goes up. So there's never such a thing as a free lunch. And it turns out that if we chose one of the lambdas, the one corresponding to the smaller norm, to be 1, that produced the best results. So the best things are things like pairs like 1, 2, 1, 3, 1, 4, and so on and so forth. And this is strictly experimentally determined, right? And so we ran these numerical experiments, and then on a smaller scale, and then we determined from those which lambda pairs seem to be the most optimal ones. And then we ran our large scale computation on those optimal lambda pairs. So that was another sort of parameter tuning exercise that we did. And then what about this extra improvement where you use sieving for factorization versus just unassisted factoring? So for n equals 3, for 3 class rank, the unassisted factoring wins. And that is because the yield of the algorithm is really high. So you find a lot of relatively small discriminants where the 3 class rank is already 2 or above. And the things that you need to factor are pretty small. And the sieving is just not worth it. You just factor them. Okay. For n equals 5 and 7, the sieving won. So there the sieving started kicking in and actually yielded a faster factorization method than just unassisted factoring. And then the bizarre thing is, for n equals 11 and 13, the unassisted factoring won again. So sieving wasn't any good for that. We have no idea why. So we thought that maybe as the n class rank gets bigger, the sieving gets better and better, but no. So this is something that we still need to look into and understand. Like what here, it's pretty clear why sieving doesn't work well. Here you can sort of imagine why it works well, but we have no idea why it didn't work for this one. So there's still sort of things that we don't understand about this algorithm. Okay, so here's now our algorithm. We implemented this in Sage Math, and the class group computations that we did were done via PowerGP, via the function called quad class unit. So you can call that from within Sage. And here's the lambda pairs and the parameters that we did. So for 3 class rank 3, we just ran the expanded search without the independence test. We still just sort of used the explicit condition to guarantee ideal independence. These were the lambda pairs. This is our biggest bound on M1. I think this is something like 2 to the 14. Sieve bound doesn't apply. For n equals 5, these were determined to be the best lambda pairs. This is our power of 2, the biggest bound on the bigger norm. And the sieve bound, this was experimentally determined to be, the best bound was determined to be twice the bound on M1 plus 7. And then similarly for 7, we use these sieve pairs and the slightly smaller bound. And again, the sieve bound was determined to be this. Here again, we didn't apply sieving. These are our norm bounds here. And here, in this case, we actually just ran the whole thing on as many lambda pairs as we could. So we used a total of 63 lambda pairs, all the ones where lambda 1 and lambda 2 are between 1 and 10 and coprime. So that's 63 pairs. So that's the search that we did. So this is the entire algorithm that we did. So this is a massive, massive, massive computation. We used the University of Calgary's advanced research computing infrastructure. So in essence, it's a big cluster. It's got 239 nodes. I forget the individual specifications, how much memory and stuff, but it's just this massive parallel cluster, and you just use the entire cluster and let it run. And let me give you approximate figures. So we ran each n for about a week, and then we stopped it. I mean, you can run this forever, right? But at some point you get so bogged down with class group computation and stuff, you just stop it. For n equals 3, we stopped earlier because we found so many discriminants that we ran out of memory to store them. So for n equals 3, this algorithm is like a firehouse. It spits out discriminants at an unbelievable rate. But as the n class rank increases, it gets a little bit more manageable. All right. And now here, these are approximate figures. Our paper has exact figures. So for n class rank 3, we found about 20 billion discriminants of 3 class rank at least 2. The search time, so what does this search time mean? So this is a massively parallel computation. If you took that computation and instead of running it on 239 nodes, you ran it on 1 node, it would have taken 6.4 months. We computed class groups for all the discriminants, and if you had done that on 1 node, it would have taken 3.8 years. Okay, and then similarly here, the numbers go down. For 5 rank, we found 1.3 billion discriminant, for 7 rank, 400 million. Even for 13 rank class rank at least 2, we still found 5 million discriminants. You see here that the search time starts increasing, but the class group computation time is still dominant. And it gets so expensive that at some point, we didn't compute all the class groups anymore. At some point, we just stopped computing class groups. So for the smaller ends, we computed all the class groups to just check explicitly what the 3 and 5 class rank is. But here we only did it for a proportion of them, about 300 million, 10 million, and then here 2.5 million. And even that takes a long time. It just starts taking too long. Okay. And this is what we found. So as I said, we found many, many new examples of discriminant delta where the n class rank for the n's that we considered is at least 2. The new records, we found a new minimal discriminant, the smallest discriminant of 5 class rank 4. There were examples of 5 class rank 4 known before, but the discriminant was bigger. We found the first examples of discriminants with 7 class rank equal to 4. We found 67 such discriminants. The smallest one is this discriminant here. This is the smallest discriminant that has a 7 class rank of 4. And one of the things that hadn't really been done very much before is we found a lot of very interesting class group structures, very rare class group structures. And I just gave a few sporadic examples here. So for n equals 3, for example, we found a class group. This is as class rank 5, 3 class rank 5, and there's a 3 to the 9 in here. Here's one 3 to the 7 times 3 to the 5 times 3. So this is the 3 solo subgroup of the class group. So this is a cyclic 3 to the 7 by cyclic 3 to the 5 by cyclic 3. And here for 13, this is a cyclic group of order 13 to the 4 times a cyclic group of order 13 times another cyclic group of order 13. So this is 13 rank 3. This is, I forget what this is maybe like 44 decimal digits or something. So we found some very interesting examples there. All right. So that's what we found. We have files and files and files and files of those. Now, we also, I should say, we made use of third-party stuff. We had available the tabulation data by Anton Mosinov, which I mentioned from his previous thesis, where he had computed all the class groups of discriminant up to 2 to the 40. So we had a lot of these class groups also available, but not all of them. Okay, now the last thing I want to just briefly talk about is how does our algorithm yield compare to what Cohen-Lenstra predicts? Cohen-Lenstra predicts that the proportion of quadratic fields with P class rank equal to R is roughly P to the minus R squared. So was that the yield that we got? So for that, what we did is we computed the following portion. So in the numerator is the proportion of discriminants that we found of P class rank equal to R. And in the denominator is the probability that the P class rank that predicted by Cohen-Lenstra that the P class rank is equal to R, given that it is at least 2. We have to include that because we only keep the ones where it is at least 2. And so this proportion here should really converge to 1, right? Okay, so, well, for R equals 2, it's pretty close to 1. 0.95, 0.99, 0.997, and here it's so close to 1 that we even don't include the rounding error. But then amazingly enough, when your P class rank goes up, the proportion is much, much bigger than 1. Much, 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 much bigger than 1. What that means is this is a super duper good algorithm. It finds way more than it should. Okay, I mean, most of the time when you do numerical computing, the problem is you don't find anything. Here you actually find too much. So it's a really good algorithm. It finds way more than it should. Okay, we're not really sure why that is. One of the things that we haven't done yet is that we want to do is actually look at this ratio for some smaller deltas and see if we can see maybe a trend. And if we have a downward trend as the deltas get bigger, then maybe it just means that the discriminants aren't big enough for this predicted Cohen-Lenstra asymptotics to kick in, but we're not really sure what's going on there. And interestingly enough, these geometric methods that are very, very different from the method that we used, the methods that were used by people like Leprevost and Schroff and Mestre, they show the same phenomenon. They also yield more. than they should. They don't yield as much as these methods, but they also yield more than they should. And nobody knows why that is. And Hof even commented on this back in 20 years ago or so. And he says, like, he also says he doesn't know why that is. So this is still something to look into. So let me just say a few words about where we go from here. We want to make further improvements to our search strategy. In particular, we want to use some of the geometric approaches to maybe pre-filter some of the stuff for which we compute class groups, using the work of Gilbert and Levin. We haven't done that yet. We want to revisit and improve the geometric methods. A lot of the numerical computations there are pretty old, so we want to maybe do some computations there. We want to combine the two and especially use the geometric methods for better filtering. Queer did this in 1987 for n equals 3 for his PhD thesis. The problem is the PhD thesis is written in Catalan. Catalan is a language that they speak in Barcelona, Spain. It's not even Spanish. It's spoken in this very, very small region in the world. And there's not many people who speak Catalan. And he wrote a little paper on this, but the paper is only about 4 pages long, and he just reports his findings, and he doesn't say much about how he found this stuff. Now, we've been in contact with him, and he's been graciously explaining some of this to us, but we're going to have to do a bit more homework there and figure out what he did. We want to do more computations. We would like to have, we would have really liked to have broken Lorenta and Quer's previous record on and found a 3-rank example of 7, but no such luck. That we're still hoping. There was this Bellabas method that does this tabulation for, without class groups for cubic field, for a 3-class group via cubic field tabulation. Maybe this can be adopted for n bigger than 3. Maybe we can use some of Bhargava's thesis work where he parameterizes these orders for n equals 4 and n equals 5 and so. I don't know. This is pure speculation. We might want to look at stuff in higher degree fields, cubic fields, that kind of stuff. And we might want to do the whole thing for function fields or abelian varieties. Now, we have done prior work on quadratic function fields, on Jacobians of hyperelliptic curves for n equals 3 and for n prime. But again, maybe there's more work to be done there. You can cheat. You can do this over a finite field, and then you bump up the finite field from fq to fq squared to fq cubed or something, and you can bump up the n rank in this way. But there's still work to be done there. So there's really lots of work still to be done there. So part of this is sort of an advertising strategy. If anyone is interested in this kind of computational work, jump right in and start working on this. There's really lots to do. And it fits very, very well into Kalyan's entire research program on class groups. And then maybe finding entirely new approaches to solve this problem. All right, I think with that, I will stop and ask if there's any questions.
Yes, thank you. Thank you so much, Professor Renate. So we have a little time for some quick questions. If there is any question from the room, so Krishna has some question.
So I just have a curiosity, is that you showed us some graphs earlier. In that second slide, which contains the graph, can you just go to the second slide which contains the graph?
This is where we play the movie backwards.
Yeah.
I think I went way too far.
Page 19.
There it is. Thank you. This one?
Yeah. Yes.
Mm-hmm.
Yes. In the rightmost graph, there is a peak.
There is a spike. Yeah.
Spike.
We're not really sure what that's going on there. I think it might have something to do with word sizes or something. We really don't know.
Okay, so yeah, I was just
so it's a very good question, and I kind of glossed over it, but yeah, I'm not really sure. I think Mike Jacobson is also on the Zoom call. Mike, if you have anything to add to this, maybe type something in chat, or maybe you can unmute yourself or something, but I'm really not sure.
Yeah, hi. Mike, can you unmute yourself?
Mike, do you have anything intelligent to say about this? Or have you gone to bed already? I don't think he's saying anything. Yeah, I'm not sure. We're not sure. It has to do something. It's some computation thing. It's some memory computation thing, right?
Okay. So I just have one more question. In that.
Lalit?
Sorry. In that slide. Sorry. Yeah, in that slide titled Improvement 4, Hello?
Yeah, which slide? Say again.
Improvement 4.
Improvement 4, yes.
I'm not able to find that. So I'm trying to.
Yeah, so there you are asking, instead of factoring an integer, you are asking to find the nth root modulo q.
I'm hearing someone else speaking. I'm not sure.
Yeah, just
Is someone maybe not muted?
yeah, some
Okay, yeah, I think it's good now. Yeah, sorry, could you repeat the question?
yeah, here instead of factoring some integer, you are asking to find the nth root of an integer, right? Modulo prime, if I'm not wrong.
Yeah, you compute the nth roots because that gives you candidates for the ratio M1 over M2.
Yes, so if I understand, this is a harder problem computationally than factoring an integer. That is how I understand.
But you only do it for one Q, and then you get so many other multiples of Q for free, right? Because you're getting via the sieving, you get all the other multiples of Q for free.
Okay,
So that's why it's worth it. So you have to do this effort once, but then you get a whole bunch of other stuff for free afterwards, a whole bunch of other sort of factors for free afterwards. That's why that's worth it.
Okay. Okay.
But here, this is bullet point 3 and 4, the sieving part. That's why we do this.
Okay,
Yeah.
thank you.
Mike actually just left a comment in the chat as well. He says it looks like a word size issue, no other ideas. That's what we guessed. Right? So that was about the spike that you said, yeah.
Yeah, I mean, because of the time constraint, I had to take it, but Krishna will be in touch with Renate. So if there is any question, a quick question, a couple of questions from the online participants, you can unmute yourself and then ask. We have a time for a couple of questions. Yeah, you can raise your hand and it will be unmuted from here.
Okay, I don't see anything in chat.
Yeah, so I think that is all, Professor Renate. Let's give a big hand to Professor Renate for a wonderful lecture.
Thank you very much.
And really thank you, Renate. See you soon sometime. Bye-bye. So again, Krishna, I'll hand over maybe. Or it's already time, no? Yeah, so Professor Stephen Miller is there.
Yes, how are you doing?
Yes, Professor Stephen is there. So